feel like doing this right now, but it has to be done, because I've begun Lecture 8, Assigned Reading, 4.3 to 4.6, using functions to modularize code. So far, all of the functions we have implemented have been small. They fit nicely onto a single page. As we implement more complicated functionality, it is convenient to split functions into multiple functions, each of which does one simple thing. To illustrate this idea, we somewhat superfluously split findRoot into 3 separate functions, as shown in Figure 4-8. Each of the functions has its own specification, and each makes sense as a standalone entity. The function findRootBounds finds an interval in which the root must lie. BisectionSolve uses bisection search to search this interval for an approximation to the root, and findRoot simply calls the other two and returns the root. Is this version of findRoot easier to understand than the original monolithic implementation? Probably not. A good rule of thumb is that if a function fits comfortably on a single page, it probably doesn't need to be subdivided to be easily understood. I guess that depends on how big your page is, huh? Am I right? Check it out. findRootBounds, BisectionSolve, and findRoot. Split it into 3. Pause the video if you want to look at this code more carefully. I don't think it's really necessary to break it down any more than it's already been broken. Functions as objects. In Python, functions are first-class objects. That means they can be treated like objects of any other type, e.g. int or list. You know, objects of any other type. They have types, e.g. the expression type of the absolute function passed in as argument has the value built-in function or method. They can appear in expressions, e.g. as the right-hand side of an assignment statement, or as an argument to a function. They can be returned by functions, etc. Using functions as arguments allows a style of coding called higher-order programming. It allows us to write functions that are more generally useful. For example, the function BisectionSolve in Figure 4-8 can be rewritten so that it can be applied to tasks other than root finding, as shown in Figure 4-9. We start by replacing the integer parameter power by a function eval_ands that maps floats to floats. We then replace every instance of the expression ands **power ands to the power by the function call eval_ands, or by the function call eval_ands with ands passed in as argument. If we wanted to use the new BisectionSolve to print an approximation to the square root of 99, we could run the code like this, where we define a function called square, which has one parameter, ands, and it returns that whatever's passed in as argument to this parameter ands to the second power, and then it assigns simultaneously values to 2 variables, low and high. Those values will be the output of putting in 99 and 2 as arguments to the findRootBounds function. Finally, print BisectionSolve with 99 square 0.01 low and high passed in would apparently print an approximation to the square root of 99. It's 5:30 in the morning, and I'm just taking their word for that. Going to the trouble of defining a function to do something as simple as squaring a number seems a bit silly. Fortuitously. It's a $10 word to use in place of fortunately here, huh? Fortuitously, Python supports the creation of anonymous functions. i.e. functions that are not bound to a name, anonymous, using the reserved word lambda. The general form of a lambda expression is lambda sequence of variable names, expression. For example, the lambda expression lambda x, space y, space x star y, lambda x, y, x star y, returns a function that returns the product of its two arguments. So it's saying, we got two parameters here, and what it will return is whatever's passed in as arguments in those parameters multiplied by each other. Okay, lambda expressions are frequently used as arguments to higher order functions. Sorry. For example, we could replace the above call to bisection solve with a call of the print function with bisection solve calls the call to bisection solve passed in as one of the arguments here. And one of the arguments passed into the bisection solve call is itself a lambda function, which has this parameter ants, and whatever you pass in to ants, what does it do to it? Squares it. Finger exercise. Write a lambda expression that has two numeric parameters. If the second argument equals 0, it should return none. Otherwise, it should return the value of dividing the first argument by the second argument. Hint: use a conditional expression. Since functions are first-class objects, they can be created and returned within functions. Shit, I drank too much coffee just now. For example, given the function definition here, if our function create a val ands, just has no parameters, and the definition of which a variable power is created and assigned the value, which is the output of the input function, given enter a positive integer, and then returns the output of a anonymous lambda function, which will take in ands and use the converted to integer output or value of power as the exponent upon it. The code eval ands set equal to create eval ands, followed by call to the print function with a call to bisection solve function passed in as argument, and as passed into argument to this 99 eval ands 0.01 low and high, will print an approximation to the nth root of 99, where n is a number entered by the user. The way we have generalized bisection solve means that it can now be used not only to search for approximations to roots, but to search for approximations to any monotonic function that maps floats to floats. Monotonic is a function from numbers to numbers is monotonically increasing, decreasing. If the value returned by the function increases, decreases, as the value of its argument increases, What? A function from numbers to numbers is monotonically increasing, in other words, decreasing? If the value returned by the function increases, decreases? I guess, are they just saying it's monotonically increasing or decreasing if the value returned by the function increases or decreases, respectively? It's a terrible way to say that. Don't do that in just parenthetical assigns. What the hell? Okay, we're back. For example, the code in figure 4-10 uses bisection solve to find approximations to logarithms. Check it out. This approximates logs. I don't know, it's like a piece of a tree. It's approximately a log. Notice that the implementation of log includes the definition of a local function, find log bounds. This function could have been defined outside of log, but since we don't expect to use it in any other context, seemed better not to. I guess let's take a look at this real quick, okay? Good enough. Methods. Oversimplified. Methods are function-like objects. End of section. They can be called with parameters. They can return values. And they can have side effects. They do differ from functions in some important ways, which we will discuss in Chapter 10. For now, think of methods as providing a peculiar syntax for a function call. Instead of putting the first argument inside parentheses following the function name, we use dot notation to place that argument before the function name. We introduce methods here because many useful operations on built-in types are methods, and therefore invoked using dot notation. For example, if S is a string, the find method can be used to find the index of the first occurrence of a substring in S. So if S were, for instance, ABCBC, the invocation s.find, and then in parentheses the string BC would return 1, because it is at index 0, 1 that we find the first instance of this substring passed in, BC. Attempting to treat find as a function, e.g. invoking find with s not placed in front with dot notation, but instead as the first argument in the parentheses next to it, like a normal function, will produce the error message name error. Name find is not defined. Finger exercise. What does s.find sub return if sub does not occur in S? Finger exercise. Use find to implement a function satisfying the specification def find last, s and sub as parameters, and the stock string explaining what you should put in here. S and sub are non-empty strings. Returns the index of the last occurrence of sub in S, and returns none if sub does not occur in S. Figure it out. Terms introduced in chapter: function definition, formal parameter, actual parameter, argument, function invocation, function call, return statement, point of execution, lambda abstraction, test function, debugging, positional argument, keyword argument, default parameter value, unpacking operator, star, namespace, scope, local variable, symbol table, stack frame, static, lexical, scoping, stack, last in first out LIFO, specification, client, assumption, guarantee, decomposition, abstraction, docstring, help function, first class object, higher order programming, lambda expression, method, dot notation. Lecture 8 assigned reading complete.